co-chairs and Dr. Robert Fovell and Qinghua here, and the first talk is given by Robert Fovell on the topic of sub-microphysical contribution to typhoon motion, structure, and intensity. Dr. Fovell is from the Department of Chemical and Oceanic Sciences of UCLA.
Thank you. Can you hear me? Okay. All right. First of all, let me give you a little bit of background. Okay. What you're looking at the top is basically these were forecast hurricane tracks from Hurricane Rita, which was a storm in 2005 that reached the U.S. Gulf Coast. So this is Texas. This is Louisiana. New Orleans is here. 3 weeks before Hurricane Rita came ashore, Hurricane Katrina made landfall just east of New Orleans. So basically what these represent is simulations from a variety of different models. And these models are different with respect to their character, their resolution, their degree of sophistication, all sorts of other things. They use different initial conditions. They use all sorts of different kinds of model physics and things like that. And basically each one gives essentially a somewhat different track. And what we had done is we had done simulations starting at exactly the same time, but using one model, the NCAR version of the WRF model, and one initial condition, which came from the Global Forecast System model. And what we did is we varied physics relating to convection. So that is basically cloud microphysics, cumulus parameterization schemes, things like that. And so what we got was, okay, so this has been happening all day and I'm going to do it too. But, so we got a whole big variety of tracks here, basically from a single model and one initial condition, but just varying things relating to model physics relating to convection, okay? So we wanted to see if this was a fluke, and actually we determined that it was not for the 2008 season in the Atlantic for 5 different hurricanes that made landfall in the United States. And what we did is we took 68 simulations, okay, of these 5 different cases, and for each simulation we made 12 model runs using different combinations of cumulus schemes and microphysics schemes. And basically this is just one of those cases representing Hurricane Ike, which also made landfall along the US Gulf Coast in Texas. And basically what you're seeing here is there are 12 ensemble members here, and they give quite a spread of tracks, right? And these are the hurricane center tracks that are basically from the model initialized at the same time. So these are many different models. This is one model varying cloud microphysics and cumulus parameterization schemes. And the good news is that the spread is very similar. The better news is that was true amongst all of these 68 cases. The bad news is in this case, everybody is wrong because the black dots were the actual position. But we were all wrong in sort of like the similar way, okay? So we've been doing high resolution, idealized simulations in an attempt to try to understand why all of this is happening. And so basically, we need to lose this thing. Okay. So anyway, these are idealized WRF simulations representing 3-day simulations, either 3 or 4 kilometer grid spacing depending on the particular study. And what we tried to do is use the real data WRF that was as similar as what might be used operationally as possible, but simplify it. Simplify it by removing all of the large-scale variability, replacing it with a single sounding, removing all of the land, and removing all of the wind and everything else, and just starting with something that's very idealized and something that is simple, okay? So we're basically using the real data WRF, but initialized with the Jordan hurricane season sounding, initially calm, no land, and a uniform sea surface temperature. And what these represent is 6 tracks from 6 different bulk microphysics schemes. And this one, what I'm going to call K, is basically just a warm rain scheme. It's cloud water and rainwater. W is a simple ice scheme. Basically, if you're above or below the freezing level, you handle condensed water differently. L and W6 are 5-class ice schemes, which basically have 3 forms of ice, like ice crystal, snow, and graupel. And S1 and S2 are two different versions of a very sophisticated, in this case very sophisticated means really expensive, two-moment microphysics schemes. And basically all of these give you essentially these tracks. So we start here at this point, start with a coherent initial condition that is shared by all of these simulations, and we get all these variety of tracks. You may wonder, why is Taiwan being sketched on here? This is to give you a sense of scale. Okay, there is no land in the model, so there is no landfall. Okay, so basically we've got very different tracks here, and so what we've tried to do is to understand why this is happening, and this picture at the bottom here is part of the reason. What we've done is we created these symmetric components obtained via vortex following composites. So these represent the radial structure of the 850 millibar wind speed. This is radial distance from the eye out several hundred kilometers. This is the wind speed, and for three of these tracks, these are the wind components, okay? And of course, there's difference with respect to intensity here, but what we were focusing on is the wind field at relatively large radius that controls the advection of planetary vorticity and thus the beta drift of these particular cases. So, and this was very similar to research that Russ did a number of years ago. This is longitude versus latitude, and these are three different tracks that result from basically three different radial profiles. Changing the winds at larger radius changes the track. Okay, so if we manipulate the microphysics, and there's almost an infinite number of ways of manipulating the microphysics, we can change the track, and this is an example of that. Here, again, this is longitude versus latitude, and I realize I forgot to sketch Taiwan on here for you. But these are three different tracks that represent taking a microphysics scheme and playing around with the fall speed, either making the fall speed larger, smaller, closer to the core, farther from the core, or both, okay? And this represents taking the 5-class ice scheme and just preventing graupel from being created. One of the big differences that microphysics schemes vary from scheme to scheme, even if they have the same number and kind of condensation types like ice crystals and graupel particles and what have you. What they really differ is with respect to how much ice they produce relative to snow, relative to graupel and things like that. So we just found in this case, if we took the scheme and just decided to prevent graupel formation, we get a really big difference in the track here. And if we looked at the radial wind profiles, basically everything seems to be telling a coherent story so far. Basically what happens is I change microphysics schemes, it changes the radial wind structure, that as a result of changing temperature gradients, that changes pressure gradients, that changes winds, that changes the track through the beta drift and things like that. Okay, why manipulating fall speeds changes the storm track partly is because, as I was just trying to say, it changes the amount of convective activity at various places. These are two rather extreme examples of basically vertically integrated condensate for two cases.